Good morning, everyone, and welcome to this EXA2 Pro Eco workshop. We are very happy to hold this workshop. We would have preferred to receive you in Maison de la Simulation or somewhere else so that we could meet in person, but it's still very nice to have this workshop online. So as you know, it's a 3-day workshop. So today, this morning and this afternoon, we have the presentation of basically the framework and the tools that have been developed in both projects. So first, for this morning, we have a presentation of the main tool developed in the context of the EXA2 Pro project. This afternoon, we have the same thing for ECO. And then tomorrow and Wednesday, there will be some tutorial hands-on to learn how to use the great tools that have been developed. So a bit of practical information. So we decided not to use chat so much, but we have a pad. So Julien has put the link to the pad in the chat of Zoom. So you can click on the link, go to the pad, and the pad is meant to make the workshop more convivial. You can have a discussion within the pad, ask question, answer question. We will review it. So it will be much more convenient. And it's better because it's much easier to organize the pads than a Zoom chat. And also, please identify yourself when you're in the pad so people know who they are talking to. And we will have, of course, at the end of each talk, some question and answer session. So please leave a bit of time I'm talking to the speaker, leave a bit of time at the end of your presentation so that there is enough time for question. And I would also like to ask the speaker to keep the schedule, keep the time. They were allowed because we have quite a busy schedule today, so we don't want to sleep too much in the schedule. So we will start this first session, and this first session is dedicated to the presentation of the EXA2 Pro framework. So we first have a talk which will give us a broad view of the framework and success story of EXA2 Pro that will be given by Lazaros Papadopoulos. So please, Lazaros, yeah, you're there.
Okay.
So Julien will give you the floor so that you can share your screen. And you can start your presentation. So please try to keep within 25 minutes so that we have 5 minutes for question at the end.
Sure. Okay, thank you very much for the introduction. Let me share my screen.
We see your screen, Lazaros. It's okay.
Okay, good. Okay. Thank you very much for the introduction. Good morning to everybody. I'm Lazaros Papadopoulos. I'm a research associate at the ICCS, which is associated with the National Technical University of Athens, and I am the EXA2 Pro technical coordinator. So this presentation the focus of this presentation will be mostly on the main ideas of the EXA2 Pro success stories, results, etc. And it will be less technical since the next two presentations will be explicitly about the EXA2 Pro technologies. So the EXA2 Pro is a FET HPC project. It is about transition to exascale computing. It consists of 8 partners from 5 countries, and the budget is 3.5 million. And the duration is 3 years. So the project officially ends on 30th of July 2021.
Lazaros, excuse me for
Yes.
1 second, please. I will get back the role of presenters and name you co-presenter so I can keep people from the waiting room. Give me 1 second.
Yes.
Okay. Go ahead.
Okay. Can I continue?
Yes, you can. Go ahead.
All right, thank you. Okay, so the Exa2 Pro is the title of the project is Enhancing Programmability and Boosting Performance Portability for Exascale Computing Systems. And the motivation is the fact that we need to support the growth of HPC application and their transition to exascale computing, according, for example, to the strategic research agenda by the ETP for HPC. Because currently, only few applications are expected to benefit from the upcoming exascale computing systems. For example, in the US ECP project, only 30 applications have been selected to be deployed to the exascale computing system. So enabling more applications to move towards the exascale computing direction is obviously very beneficial. So the main goal of the Exa2 Pro is to promote and lower the barrier of access to exascale computing systems to the scientific community and industry. And how do we contribute to that direction in the Exa2 Pro? So the exascale systems are expected to be heterogeneous, to integrate different kinds of accelerators. So the Exa2 Pro improves the programmability of heterogeneous computing systems by hiding their complexity from application developers. And let me try to be a little bit more specific. So one objective of the Exa2 Pro is to follow a single source, multiple backend approach. So in the Exa2 Pro, we integrate a tool that provides various different patterns of computation implemented for a variety of backends. And these are the skeletons. Example of skeletons are MapReduce, stencil computations, etc. And each one of these skeletons is implemented for a variety of backends. For example, OpenMP, CUDA, multi-GPU, StarPU MPI. And this is basically the SkePU Exa2 Pro tool, which is the Exa2 Pro high-level interface. And the idea is that developers are expected to implement computations of their application through the SkePU Exa2 Pro tool. But I need to clarify that, okay, this is the main idea of SkePU. However, SkePU has several other interesting features. For example, these backend implementations are tunable, etc. But you will hear more about this during the next presentation, which is specifically about SkePU. And you may also have some hands-on experience tomorrow morning in the SkePU hands-on session. So this single source, multiple backend approach has several advantages for application developers. For example, developers can experiment with different platforms and accelerators, OpenMP, CUDA, OpenCL-enabled accelerators, etc. And also, they can directly use the backend implementations already provided by the Exa2 Pro SkePU tool. And this significantly contributes to productivity. It means that the developers do not need to write CUDA code because the CUDA code is already there to be used. And this is a very nice example in which we applied SkePU effectively. So one of the Exa2 Pro applications can be used to design material and processes for CO2 capture. It is from the domain of chemical engineering and materials. So we applied SkePU to this application to parallelize a part of the application that was originally sequential. And indeed, we achieved very nice results, 41% reduction in execution time. However, the skeleton that we used from SkePU to apply to the application, the map skeleton, provides also a CUDA and OpenCL implementation backend. So the developers, the application developers, were able to evaluate the application on a GPU. And this is something that they actually wanted to do for several years, but they had neither the expertise nor the resources to do it. After all, they are chemical engineers, and their expertise is chemical engineering. They are not computer scientists. So they managed to evaluate a GPU port of their application by using SkepiU. And this is a nice example that shows how the accelerators can become more accessible to developers and how we can contribute to the transition to systems that use accelerators, such as the exascale computing systems. Of course, an obvious question is, okay, what is the effort to apply the Exa2 Pro interface in an application? The SkepiU tool can be used, first of all, as a library, okay? And the amount of effort, of programming effort that is required to apply it depends a lot on the kind of application and on how well the application algorithm matches the computational patterns offered by the Exa2 Pro interface, by the SkepiU. So, however, to apply the interface is easier in cases where the application is developed in C and C++, because Fortran is still only partially supported by the Exa2 Pro framework, and when the computational kernel is well isolated. It's easier to replace the computational kernel, in this case, with the SkepiU interface. Of course, the Exa2 Pro offers several other features. For example, the elimination of suboptimal or non-applicable backend implementations at design time. So only a subset of these backend implementations is forwarded to the runtime system of the Exa2 Pro. The runtime system of the Exa2 Pro is StarPU. And then StarPU can select the most efficient implementation at runtime. So it can switch at runtime between different implementations, depending on the execution context, depending on the availability of resources, considering also performance and energy consumption as optimization criteria. More about this during the presentation after the break, which is specifically about the StarPU and in the StarPU hands-on season, the last day of the workshop. Another objective of the Exa2 Pro is to support a co-design approach, to follow a co-design approach between tools and applications. So the Exa2 Pro tools, such as StarPU and SkepiU, originate from the general purpose computing domain, and they evolved through several projects. Now, in the Exa2 Pro, these tools evolve towards the exascale computing direction by following this co-design approach between tools and applications. And this is a nice example of co-design. So we applied SkepiU to a neural simulation application, a brain modeling application, and we applied the map skeleton. We used the MAT data container provided by SkepiU as input to this skeleton. And as you can see in this red line, the scalability results were rather poor. So the SkepiU developers developed a new skeleton, the MATROW skeleton, which, as you can see in this green line, significantly improves the scalability. So they developed, let's say, an application-specific data container to improve the scalability of the application. So this is a nice example in which the tool evolved to support, to provide better results for a specific application. It's an example of co-design. Another objective in the Exa2 Pro project is to evaluate the data flow programming model. The data flow programming model is used to program the FPGA-based Maxeller data flow engines, the DFEs. Maxeller is a partner in the Exa2 Pro project. So we ported one of the Exato applications, the MetalWorks application, which is a simulator for supercapacitors to a DFE. And the results were quite impressive. Performance improved by 4 times, energy consumption lowered by 10 times, and we achieved 50% higher performance per watt compared to a P100 GPU. However, the development time required to implement this port was 8 to 12 months. And we are talking about skilled senior engineers from CNRS. So this highlights the fact that we need tools to improve the productivity for accessing accelerators. Currently, DFE is only partially supported by the Exato Pro framework. In fact, it is supported by the runtime system, the StarPU, but not yet from SCEPU. This is an ongoing work. Because the data flow programming model is quite different from the programming models that already used in the Exato Pro framework, skeleton programming and task-based programming model by StarPU. And the next step is to use MetalWorks with StarPU for multi-DFE experiments. This is an example how we exploit accelerators with the use of advanced tools and programming models, and more specifically StarPU in this case. So this is the Exato Pro stack. The application is on the top. The high-level API and software abstractions, which is actually SCEPU. Then is the composition framework and optimizations. You will have the opportunity to hear more about SCEPU and the composition framework, the ComPU, during the next presentation. There is the runtime system, which is the StarPU, and the hardware. And just a few information about the Exato Pro applications. So in the Exato Pro, we have 4 applications. The LQCD, the Lattice QCD, and the KKR Nano are 2 applications provided by the Jülich Supercomputing Center, and their applications deployed in pre-exascale systems that target exascale systems. And the goal for these 2 applications, the main goal, is to evaluate, to port them on DFEs and evaluate the data flow programming model for them. And we have also materials and processes for CO2 capture and MetalWorks, which is a supercapacitor simulator. These applications are basically HPC applications deployed in clusters, and the goal is to evaluate them in larger systems and evaluate different kinds of accelerators for them and programming models through the use of the Exato Pro tools. Another aspect that we're looking at in the Exato Pro project is the software engineering practices in HPC. So it seems that there's an increased number of studies in the HPC domain related to software engineering practices, as you can see in the figure here. And most of the studies refer to the implementation and the testing phases of the application development phase. So in the Exato Pro, we developed a tool for improving the maintainability of HPC application. It supports C, C++, and Fortran. And what this tool actually does is that it statically parses the source code of the application and suggests optimizations, not so much optimization, minor refactorings and modifications in the source code to make the source code more maintainable in terms of software engineering, based on some software engineering metrics. This maybe does not make so much sense for legacy applications, but it makes a lot of sense for applications that are currently under development and we want to keep them maintainable. Okay, so the last slide is about the conclusions and lessons learned from the Exato Pro project. So tool support for accessing accelerators can significantly improve the productivity of application developers and there were several examples about this in the Exato Pro project. We found out that the interaction between tool developers and application providers was indeed very constructive because it contributed to the maturity of the tools and also to the application performance improvement in several cases, such as the CO2 capture. And finally, the data flow programming is difficult, it's challenging. However, the initial results are very promising. Okay, thank you very much. And I'm available to answer any questions.
Thank you very much, Lazaros, for the very broad overview of the Exato Pro project. And we are now really looking forward to go deeper into all these tools. Are there any questions you can use in the Zoom tool? You can raise your hand. So please, if you have a question, raise your hand. Yes, Mathieu, please.
Yes, thank you very much, Lazaro, for this presentation. Just Edward, don't forget to look at the Framapad in case there are interesting questions.
Sure.
So I have two questions. First, how do you compare the SkipEU system with all the new programming models we have now, such as Cocos, Raja, DCP++? Is there a possible comparison between these two systems?
Yes, of course, the accelerators, the exploitation of accelerators is a very challenging thing. So indeed, there are there was a variety of tools and approaches that try to make accelerators more accessible. There is not a direct comparison, of course, so far, but in the SkipEU, we'll try to follow a more, let's say, generic approach and to try to support multiple accelerators and programming models that are not maybe yet supported by other libraries, for example, the TFEs, the data flow programming model.
Okay.
Mm-hmm.
Okay. But I have another question, if possible.
Yes, please.
It's about OpenCL. So I read some papers these last few years about OpenCL, and I have the feeling that OpenCL is a kind of is lagging behind in terms of performance, but also is less supported. It's not as supported as it should be by the vendors. And I have also the feeling that the vendors like NVIDIA, Intel, AMD, they are pushing more their own platform than trying to collaborate with OpenCL. What's your impression about this?
Well, yes, a good thing about OpenCL is the fact that it is also supported by FPGAs. And so this makes a very interesting programming model because CUDA is specifically about NVIDIA. So this is the reason that maybe also for the next presentation, the developers of Skepo can also very well analyze this even further. But the goal is to support as many in the Exato Pro, as many programming models as possible to make it, to try to improve the portability and programmability of application developers as much as possible.
Okay. Thank you.
Thank you. Okay.
Any other question? We have time.
Maybe I can ask a comment about OpenCL. What we have heard is that OpenCL indeed has usually provides less performance than the dedicated programming model of the manufacturer, but at the expense of portability. I have seen some discussions like Ronan Cariel showed that, okay, with OpenCL, you have less performance, but you have portability and you don't have to spend yet more time when you go to another platform and another platform each time having to tune your program. It's really not the best performance, but it's reasonable, and it saves engineer time. And that, depending on your situation, you might prefer to spend engineer time to port to the programming model of the manufacturer, or stay with the portable version and not have to spend this.
Okay, thank you.
Okay. But oh, sorry, if there is another question, I will let.
Okay, you have a question, Mathieu?
Oh yes, if there is no more question, I have just and so you don't think that in the future maybe OpenCL could start dying slowly if some programming models like Cocos becomes more and more popular, since Cocos has the target as the goal to cover a broad number of accelerator. Of course, so far they don't target the FPGA, but they can they can target the AMD, the Intel, and the CUDA, the NVIDIA systems. So what do you think about this?
Well, yes. Maybe.
I don't want you to. It's a really open question. I don't have any
Yeah.
opinion. So it's really to understand the.
Yes, at this point, I mean, the goal, yes, indeed, is from Exato Pro perspective. OpenCL is still, I mean, quite popular. I mean, the fact that it is portable across a wide variety of accelerators, FPGAs, GPUs, is very important. So at this point, we are interested to support, in the context of the Exato Pro, OpenCL, and this is what we try to do. Now, in the future, yes, indeed, if OpenCL dies, then it be replaced by another programming model, I think that the Exato Pro developers will, the tool developers will have to adapt to that. Yeah.
Okay.
Personally, I don't think OpenCL will die anytime soon. I mean, like 5 or 10 years ago, we were already saying, okay, there is OpenCL, but it's not clear that it will stay because it brings less performance, etc. And still it is there, and some people advocate the use of it.
Okay.
So yeah, it might just stay here, not being a prime target for performance, but still being there for portability.
Okay, so it's still interesting to consider OpenCL for new applications. Okay.
Mm.
Thanks.
Okay, thank you very much again, Cesaros, and I guess
Thank
now
you.
we'll move to the next speaker. So now we will go deeper and in more technical detail into the Exato Pro tools. And so the next speaker will be Christoph Kessler. And so he will develop and present in detail the high-level programming interface that were just mentioned, so SCAPU and CompU. So you can have more details on this interface. So Christoph, the floor is yours. I think
Thank you.
Julian will make you presenter.
Yes, I'm in the process of doing it.
Yeah.
In 1
And
second.
could you please let me share my screen because
Yeah.
it's
Yes.
disabled? Yeah, so welcome everybody, and thanks for inviting me for giving this presentation. I'm Christoph Kessler, Professor for Computer Science at Linköping University in Sweden, one of the partners in the Exato Pro project. And I would like to present about the high-level programming interface of Exato Pro, and especially elaborate on two technologies, SCAPU and CompU, where SCAPU is the one that we are also going to dive deeper into tomorrow in the tutorial and hands-on session. Now, the high-level programming model's objectives are, well, to handle the hardware complexity of modern HPC clusters, which essentially contains heterogeneous architecture in the different nodes, and also software complexity is increasing. So it would be good to bring these two together and find a good solution here. And so our approach is to raise the level of abstraction, which should benefit program productivity, it should benefit code quality, it should benefit portability, and it should also help with the integration of tool chains, so that we do no longer need to well, deal with individual platform-specific tool chains, but maybe have a single source and a single button to push. Now, the interoperability with traditional HPC programming models is certainly also important. So we try to reuse already pre-parallelized source code, of which there is a lot around already in the HPC community. It would be a waste of engineering effort to just throw them away and begin from scratch in the re-implementation. So if we have a good MPI ports already, then we should consider maybe using them and extending them rather than throwing them away. Yeah, we have aspects such as performance, fault tolerance, heterogeneity. So our approach comes in 4 pillars, if you could say, this high-level programming model of Exa2 Pro. The first one is, yeah, maybe also the emphasis during this workshop, the multi-backend algorithmic skeletons, which Lazarus already briefly mentioned in his introductory talk. And together with the skeletons, also the abstractions for the operand data, which we call data containers or smart data containers. And then I will also elaborate a bit on the multivariant components, which is a kind of escape mechanism for cases where the skeletons do not fit so well. And finally, there's also a platform modeling framework, which comes with the high-level programming framework, and I will cover that in as far as time permits. So let me start with the high-level programming with algorithmic skeletons. So what is a skeleton? Well, a skeleton is a predefined generic program building block that is based on a so-called higher order function. So it has its roots in functional programming. And a skeleton is, it models a common computation or dependence pattern. And it can be customized with problem-specific sequential user code. So by plugging in such a user function, a problem-specific user function into such a generic program building block such as map, we can essentially build, we can generate an executable function, which now can be used like any handwritten source code function and just be used at runtime like any of those. Now, the big advantage of using skeletons is that they come with a number of different platform-specific implementations, which are hidden behind the interface of the skeleton. So we have things like parallelism, heterogeneity, memory management, and so on. This is not visible for the high-level programmer, but we have these implementations in the skeleton code itself. So it will also be inherited by the generated what we call a skeleton instance, this executable function. And this exposes a sequential interface to the programmer. So the programming curve for the end programmer should be fairly smooth. And this is a concept which is not new, of course. It has been pioneered in the late 80s, developed by quite a number of frameworks, mostly in Europe, by the way, in the 1990s and early 2000s. and is still very actively developed in the research community, and we are one of those efforts. Now, this has also been adopted by industry, especially when multi-core became hot about 15 years ago. And we see that, for instance, in frameworks such as Intel TBB, there are constructs which are called, well, something else. They are called algorithmic templates, but they are essentially skeletons. And also NVIDIA has its skeleton library called Thrust. There is MapReduce in Hadoop. There is Apache Spark and so on. So they are all based on the same principle, only they don't call it skeletons, but it's essentially that. Yeah, so Skepu is our framework, which we have developed for skeleton programming over, well, the last 10 years now, over a couple of projects. And so it's based on C++11. Its implementation is based on a template metaprogramming include library together with a source-to-source precompiler. And it comes with a number of predefined skeletons, including, well, MapReduce, the usual suspects, but then scan, then a map overlap for stencil computations, and also a number of, well, more application-specific or domain-specific skeletons. The skeletons in Skepu are fully variadic in both element-wise, in random access, and in scalar operands. So it's not like in some other skeleton frameworks where you have to specify the arity and you get a new skeleton for every different arity for unary, binary, ternary, and so on. But this is fully variadic here. It makes the programming interface very compact. And also the data is abstracted into data containers, which look similar to the STL data containers. So here we have vector, matrix, tensor, 3-dimensional and 4-dimensional tensors as the main data types. These are complemented by so-called, what we call container proxies, which model operand data access inside the user functions. That is the code that we plug into the skeletons, so that we can restrict the amount of elements that a user function is actually going to access. And this is important for efficiency, so that we can reduce the amount of communication that is necessary to, and well, more about that in tomorrow's tutorial. Now, there are multiple backends that come with each skeleton, and by default we support 4, namely C, OpenMP, OpenCL, and CUDA for a single node execution. Also, there's multi-GPU support. There is support for hybrid execution that uses a multi-core CPU and one or several GPUs together. And newly implemented in Exato Pro is the cluster backend on top of the StarPU MPI bindings. Now, Skepu itself is tunable for time. I will show in a minute, and also for energy, which has been demonstrated in a previous project. And it's an open source effort, so you can access the entire source code on GitHub. Now, Skepu is C++ based, so it's every Skepu program actually is a valid C++11 program. What you see here is a tiny example which implements a dot product, just to make it fit one slide. We have here 2 functions, add and multiply, which are the functions that we would like to plug into a skeleton to instantiate it into an executable function. And you see these are like ordinary C++ functions. They are a little bit restricted. They have to be side effect free, and they should not do I/O or memory allocation or some other things with global side effects. but they are just plain C, C++ and are platform independent. So the precompiler can generate platform-specific variants from these as it processes the source code. And in the main program here, we have allocated 2 data containers for the operands. So we use vectors here, which are generic in the element type, and we instantiate then a MapReduce skeleton, which is supposed to take 2 element-wise accessed operands. So we have this variadic arity option here, and we plug in 2 user functions, one that describes the element-wise combinations in the map part of the MapReduce pattern, and then we have the addition, which is used to accumulate in the reduce part of the MapReduce pattern. And we give this, this object, this function object, which is built here, a name, which is called .prod. And from now on, we can use .prod like any handwritten function, C++ function, and for instance, call it like in this example here. So that's a skeleton instance. Now, now this is a single source code from which we actually get a lot of implementations for free. So of course, sequential execution is supported by one of the implementations of MapReduce. Then there is OpenMP, there is MPI execution, there is CUDA implementation, there's OpenCL, there is hybrid execution, multi GPU, and on the plan we even want to finally have a DFE implementation. Now it only works indirectly via CompuU. But the advantage is that we don't have to manually write all those different implementations anymore. And just by the skeletons having multiple backends, we get those implementations for free. But we just live with a single source, which is not cluttered up with any platform-specific housekeeping code, like all these memory management and operand transfers and platform-specific variants of functions and so on. So all this is abstracted away. And it even gives us additional benefits. For instance, for a call to a skeleton instance, like our .prod example, we now have the choice actually at runtime between those different implementations. And depending on the problem size and maybe where the operands currently are located in the memory hierarchy, it might make sense to execute such a call sequentially on CPU or multi-threaded on CPU, or to use a GPU with CUDA, or maybe to use OpenCL, or to use multiple GPUs. And this is controlled by a performance model, which Skepo can build on its own, or it could also alternatively delegate this to the runtime system. But by the standalone version, it does it on its own. It's also, of course, possible to pre-select a specific backend manually, for instance, for measurement purposes or for debugging purposes, or just because you know best as a human engineer. And you can either set a general default, so it applies to all the calls in the program, or it can be call specific, so that, for instance, to try out different backends and compare them performance-wise. Now, I mentioned that every Skepo program is also a valid C++ program, but in order to use those additional backends, which might require very specific forms of the code that you plug into the skeletons, like for OpenCL, for instance, or for CUDA, then we have to use the so-called precompiler, or source-to-source compiler, which is in the standalone version of Skepo based on LLVM Clang, and in Exa2 Pro we have the choice between Clang and the Mercurium compiler by Barcelona Supercomputing Center, which we all have adapted for this project. Now, the precompiler converts processes the source code, modifies it, generates additional variants of the user function, and performs a few adaptations. But in general, it's not so excessive modification of the code. And then this modified source code is handed over to the backend compiler, which also links with the Scapul runtime library, which contains these data containers, the different backend implementations, and so on, creating the executable. So if you don't use pre-compilation, you still can execute Scapul code, and it will have the same behavior, but it will execute sequentially. All right, now there are a number of additions that we made during the X02 Pro work on Scapul. One of the new features is multivariant user functions. So it allows to plug in functions that not only apply to a single element of a vector, a matrix, or some other data container that the Skeleton instance would be working on, but you can have such user function variants that can apply to multiple elements at a time, to groups of elements that are consecutive. And they can also be platform specific as an optional extension. So it's not something that will break portability, because there is always the default user function, which is platform independent and which is managed by the precompiler. But you can always you can add additional ones which are tagged with the type of platform and the constraint on the platform to which it is applicable. And for these constraints, we use the XPDL platform description language to tell the precompiler for which platforms this is applicable. And if we run the Skeleton, the Scapul code on a platform which does not fulfill the constraints, well, then these additional variants will be discarded. Okay, more about that in tomorrow's tutorial. Another change, another addition that we did to Scapul during X02 Pro was due to the co-design approach together with the X02 Pro applications, which also was mentioned in the previous talk. So one such new skeleton, domain-specific skeleton, is the map pairs skeleton, which applies to, which encodes a generic version of a so-called outer product, which can take an arbitrary number of 1D vector operands along either dimension of a two-dimensional domain. Right, and so this can be combined in an arbitrary way as encoded by the user function. So this is a new skeleton with a new interface, and more about that in the presentation tomorrow. There's also a version with included reduction. Now, more about the data containers to abstract the actual operands on which the skeletons operate. They are extended generic STL-like containers like vector, matrix, and so on. They perform a number of optimizations automatically under the hood, and this is why we call them smart. Well, it's just a name, but for instance, one of them is software caching with memory coherence management. So we could, for instance, leave data or part of the data on device after having executed and computed it on an accelerator device, and only send it back to main memory if requested, if needed there, either by the programmer, for instance, for an I/O operation, or by a subsequent skeleton computation, which needs to have the data in main memory again. Yeah, so this is transparently handled by the container implementation, and to the user, it looks basically like just ordinary code, sequentially consistent at the level of a skeleton instance. instance calls. Well, if you have CPU code like I/O operations, MPI calls, and so on, which might interfere with that, we have a construct which allows to control memory consistency. So the actual memory consistency model in Skepu is weak consistency, but at the skeleton core level we have sequential consistency. Now, there are further optimizations like well, this coherence management can be done at arbitrary subarray level as well. There are copy plans to locate the closest overlapping valid copies, so we can also provide operands efficiently. There are optimizations for runtime locality, so skeleton calls can, for certain types of skeletons, actually be executed in a lazy way, piled up at runtime and then executed in one bunch as soon as needed to produce a result. This is a useful feature because this allows to optimize this set of this bunch of lazily executed skeleton calls to execute them in a way which better utilizes the cache hierarchy of the execution platform. It's also possible to delegate the data management to the StarPU buffers. Now, there are new container types as well, and it also was briefly mentioned in the previous talk. So there are more general container accesses like the MAT access proxy for matrix operands, which basically give arbitrary random access to any element inside a matrix operand. Of course, this means that if we have a distributed platform, that we basically need to provide all the data and broadcast it to the executing device. And if we can constrain that with a hint from the programmer, for instance, to say that I'm not interested in any element, in random access to any element of a matrix operand, but maybe only in a row, only in a column of a matrix, then we can significantly reduce the amount of elements to communicate, and this will then lead to more scalable code, as we also have seen in the example. So if we show it just by execution time, then we see that the MAT-row version of the code scales smoothly also across, well, in this case, up to 32 nodes on a Linux cluster, and while the MAT version of the code is going into a saturation phase quite early. All right. Now, Skepu has evolved over time. So this work has started in 2010 with Skepu 1, and it was part of the FP7 project Pepper. And so at that time, well, we already supported OpenCL because it was an important target platform. We use it as a compilation target in Skepu. So if we had had something more high level at that time, we would probably have had an easier life, but the interface has suffered a little bit from the need to also support OpenCL at this time. So which is C-based, and so this interface has then been streamlined a lot in the second version of Skepu, which was developed as part of another FP7 project, Access. And so then the programming interface became type safe, and the precompiler was introduced as a feature here. So we went away from those ugly preprocessor macros, which were the way to specify user functions in the first generation of Scapul. And now in the third version of Scapul, this has been generalized a lot. So we have not only more skeletons, but we also have much more generic APIs. The stencil patterns skeleton has been generalized a lot. Many of the skeletons now supply also multiple return types. We have the multivariant platform-specific user functions and a lot of other useful features. The set of containers has been extended also by domain-specific access proxy containers like METRO, or the region proxy for stencil computations. Then we have also on the backend side expanded with a cluster backend, and the memory model has been adapted in order to better control external communication, such as MPI communication. And more about MPI communication, of course, later. But basically, what we support is we can combine Scapul together with existing handwritten MPI code, which we call outer MPI. And we can also alternatively work with MPI-free code, where we then can use the MPI backend in the skeletons itself. So this is a kind of mutually exclusive scenario. If we have pre-parallelized MPI code, then outer MPI might be the solution to go. If we start from sequential or from single platform code, then the most convenient version is to use the MPI backend and get it for free. So, of course, there are cases when no skeleton fits or no skeleton fits well, and we would have to take something which is overly generic and thereby incurs inefficiencies. Now, for that, we provide the so-called multivariant software components as another pillar in the high-level programming model of EXA2 Pro. And these are, well, you could also call them multivariant functions. So functions with a specific interface, and each such function might have multiple different variants, which are written for different programming models, which might differ in the algorithm that is used internally, which could be could have different tunable parameters, which could have a lot of specific things. You could even take the same source code but compile it with different compiler flags, or apply certain compiler transformations so that more variants can be generated on the fly. So this subsumes a lot of other optimizations as well, and for that reason, well, we allow programmers to specify certain computations as componentized computations behind a function interface, and the function's interface is described in XML by a so-called component interface descriptor, and then each implementation is provided as a separate source file or set of source files in its subdirectory, and we have the different implementation descriptors which give the metadata of each such variant. And so at the bird's eye level, an EXA2 Pro multivariant component-based application consists of two types of code, or two compartments. One is so-called inner code. So this is code that is inside the components, inside the implementation variants, and the other is outer code. That is code that is not inside any specific component. In particular, the main function is always outer code, and outer code is executed on CPU only. It can be either sequential or it can can be using outer MPI, which means we have handwritten ordinary plain MPI communication operations plus component calls. So we would use these components at node level. And we also have another alternative here, which we call taskified MPI, which uses the asynchronous MPI features of the StarPu runtime system and also executes the component calls as tasks for the runtime system. And some more about that in the talk about StarPu. Now, these descriptors, they provide just the metadata, which is necessary by the composition framework to deploy the entire application. So the application descriptor, which describes the outer part of the application, contains in particular a list of all the components that might possibly be called and so need to be deployed as part of the application and all the non-component source files. Each component has a component interface descriptor, which contains the component name, the operand types, the access modes, the access patterns, the access distances, and so on. Things that are common across the different implementations. And then each implementation, again, has its XML descriptor containing metadata that is specific to the implementation, like required components that it might use, or supported target platform, selectability constraints, resource requirements, tunable parameters, source files, and so on, and all information which is necessary to deploy, for instance, specific compilation rules, specific flags, and so on. Now, this is just a short illustration of how the interface descriptor looks like. So it's XML code, quite compact, after a while one can get quickly used to this pattern. We have C-style signatures, C++ style signatures. Depending on which data types we use, we can use container data types here as well with the X2P variant, but essentially they map to actually to the Skepu containers, which are used for the implementation. And alternatively, we can also use the plain C data types as well. Also, we describe the interface with the access mode, the access patterns, and we can give a couple of additional properties. Now, what is nice is that, well, in principle, these multivariant component calls can be mixed with skeleton calls freely, as long as both use the same small data containers, in this case, Skepu's small data containers. The Skepu code has to be in the outer code, and of course it has to be pre-compiled if we want to use the backends for the additional platforms, for that specific flags are available. In inner code, inside components, we don't use any skeletons. That's not supported, and skeleton user functions also should not invoke multivariant components. This would be a side effect which would interact with the runtime system, and this is not foreseen in the execution model of Exato Pro. So the composition framework, also known as ComPU, is a whole application deployment framework which takes such a multivariant component-based application consisting of the inner code and the outer code source files and the various descriptors that have been provided. And now the first step is that ComPU analyzes the component descriptors and well, it generates a high-level intermediate representation of the metadata, which then can also be accessed by other parts of the framework. It also generates well, wrappers for the calls that interact with the runtime system, and it generates a makefile that coordinates the whole build process for the entire application. Well, these would then be compiled with the ordinary platform-specific compilers. For Scipio code and for source code of components that should be processed and should be modified, but in particular also for outer code, we allow to run them through the Mercurium source-to-source precompiler, which we have adapted from the version that is produced by the Barcelona Supercomputing Center, and so this is then this generates source code, which is then also further compiled, CPU code that is further compiled and linked together with the rest of the application into executable code. To that we add the X2P library, for instance, the container implementation and the MPI access layer, and we have the StarPU runtime system, which we also link to get a complete executable application. Now, well, time is going quickly, so I can only briefly mention that there is a platform description framework as well, which allows us to model distributed and heterogeneous computer systems as far as relevant for well, optimizations of all these well, frameworks, and also to, for instance, to specify constraints for selectability of multivariant user functions or of different component implementations. And the software the control relation is decoupled from the hardware structure, which is a feature of the XPDL modeling language that we use here for this purpose. And we also allow to model not only hardware entities, like memory or CPU, GPU clusters, but also to model software entities, for instance, libraries, which we would like to rely on and which can exist in different variants. So we can actually make the selectability of a component dependent on a specific library version being installed or not. So this is based on XPDL, an XML-based platform description language, which is modular extensible. It has features coming from object-oriented modeling like inheritance, instantiation, parameterizability. There is a model repository which can be added, which can be extended. And it's possible also to have wildcards in models where certain parameters may perhaps not be known at modeling time. And so then XPDL can generate deployment time micro-benchmarking code, which then allows to elicitate the values of such unknown model parameters at, well, on the target system at deployment time. It's available to the application at runtime, so we can query the model from the application. We can also query it from the tools because the XPDL framework allows to generate a C++ query API to which we then can link with both with the application and with tool chains that should be able to access this system model. All right, so the big picture is, well, we have already seen the basic structure in a previous talk, but well, of course, we have the HPC applications on top, and we have the hardware, an HPC cluster with accelerators on the bottom, and the task of the programming model and the programming framework is, of course, to bridge this gap. We have the runtime system, more about that in the next talk, which already comes with a specific task level programming API, So this is one way to do Exa2Pro programming, but of course it also comes with the high-level programming interface, which consists of the skeletons, which consists of the smart data containers, the multivariant components, the platform query API, and there's also support for fault tolerance at the high level, which basically wraps features that are provided by the runtime system. Now, the composition framework, which I've briefly mentioned, well, it consists of ComPU and of the source-to-source compiler, which has also an intermediate representation, which I did not go through in detail now, but this intermediate representation represents the components metadata, and it also, for each compilation unit that is source-to-source compiled, the source compiler has its own intermediate representation that can connect to this Commere representation. It's possible to extend this basic composition framework engine by plugging in special extensions which can perform granularity or locality optimizations as part of this source-to-source transformation mechanism and the wrapper code deployment. We have performance modeling possibilities, so that we can have feedback-directed optimization to run the composition framework twice, once to deploy a profiling run, which then is executed to populate the performance model in the composition framework, and then to rerun it in order to use this performance model to guide the and to possibly eliminate suboptimal implementation variants already at program generation time. Yeah, also there's some Pragma syntax available for fault tolerance management. There is more in the project which I cannot go in details here. There is, for instance, tools for analyzing and managing technical depth in the application source code. There's also some work on an IDE for Exa2Pro. What we will dive into more details now in the tutorial tomorrow is the Skeletons API together with the Smart Data Containers API, and then there will of course also be the separate tutorial on StarPU on Wednesday. So let me conclude. The Exa2Pro high-level programming model provides coherent high-level abstractions for the compact, for the portable, and for well-structured single-source code. So we inherit a lot of different implementations automatically with the skeletons and with the smart data containers. We abstract the data and we abstract away from the distributedness of the address space. Multivariant components are a way to escape for computations that do not fit any of the skeletons well. So now it's the programmer who is responsible of writing the different implementations, but still we only expose the different options to the composition framework and let the composition framework together with the runtime system decide automatically at runtime which of those different implementations to actually invoke when we do such calls. And this is supported also by the platform modeling framework. So we abstract away heterogeneity, we abstract away explicit parallelism by providing a quasi-sequential programming interface. This is what the skeletons do. Or we can also embrace heterogeneity and explicit parallelism with the multivariant components, which is a bit more effort for the programmer to produce the actual source code of the implementations and also to fill in this XML specification of the metadata. But anyway, it's declarative, so we do not hard code any platform-specific optimizations or specific backend selections, because these assumptions might no longer be true on the next generation of hardware, and so we would have to rewrite the program otherwise. So the idea is rather to go towards future-proof source code, which can automatically adapt in the best possible way to the next generation of target hardware, whatever it will look like. So SCEPU 3 is a co-design effort which is based on feedback from the Exeter Pro application partners. It is open source, and you can find more information and the source code at this web address. For CompuU, we have the integration of existing parallelizations as a feature. So OpenMP, CUDA, OpenCL can be integrated, and so wherever skeletons do not fit, we have this as an escape mechanism. Of course, where the skeletons fit, we should use the skeletons because it's much easier for the programmer. So I would like to conclude with a short remark that those of you who are going to attend the tutorial, and in particular the hands-on session tomorrow morning, which will be done together with my co-workers August Ernston and Johan Alquist from Linköping University. So if you're going to attend that, please try to complete section 2 of the instructions, that is the installation of the Docker file before this hands-on session, because the installation is expected to take approximately half an hour, and we don't want to waste time tomorrow and wait for this installation to finish. So please try to do that beforehand. So that's all from my side. Thanks a lot for listening, and I'm looking forward to your questions.
Well, thank you very much for this very nice presentation. We have a bit of time for a few questions. Please raise your hand using the participant windows of Zoom if you have any question. Yeah, Mathieu, please.
Yes, thank you very much, Christopher, for this presentation. I have just one question. If I have a code already parallelized, but not, for instance, on GPU, and I want to use the SCEPU system to port my code, what's the best strategy to do it?
Well, if the computations pattern fits any of the skeletons, then it should be quite straightforward. So what you need to do is you need to identify the part of the computation that corresponds to the skeleton's behavior. You should identify the part that is problem specific, so which you would put into the user function to plug it in. So what is done by the skeleton in a sequential program or in an OpenMP program, it would typically correspond to one or several nested loops, which you could then replace by the skeleton that you choose. Map reduce, map overlap for stencils, or map pairs, or whatever it is. Well, the code that you plug in needs to be outlined into a separate function, which then is plugged in. So that's the basic operation on the code side, and then for the operand data that you work on, they should be framed in containers. So that's the containers. It's a kind of wrapper data structure. They do not add much overhead, but it's you can construct them around existing C++ arrays.
Okay.
So it's merely, but they are necessary so that the skeletons can actually work properly, so that they can follow up. Where is my data right now? What is the validity status? And that the optimizations that the containers can perform for SCEPU actually can work.
Okay, and just to add one more question. Would you suggest to extract a kind of to extract the functions from the main code and to start a new one using the Exato Pro framework or the SCAPU framework, or can I work directly in my existing code, trying to include the map operations and the abstraction?
You can start basically from your existing code and maybe identify the hottest part of it, typically some Solver core, or where most of the performance is required, and then start with that. Identify what is the pattern and which skeleton would fit. And then you can locally replace this part by a proper skeleton instance of the right type.
Okay. Okay, thank you.
Thank you, Mathieu. Maybe I would have one more question before we go ahead to the break. Because for a code developer, it's very important to have a long-term vision and to adopt tools that will be supported on the long run, of course, because you don't want to redo your code fully once in a while. So can you give us the perspective, and if you expect to have a long-term support for this tool, and how you see the future of this tool?
Well, we are going to further develop SCAPU also beyond Exato Pro, as long as we get funding for it.
Okay. Excellent. Thanks to all of you. Now we have a short break. Well, not so short, half an hour. So please, we can reconvene at 11 to start at 11:15 sharp for the next presentation. Thanks to all of you. So I was thinking it's a bit sad to have a coffee break alone in your room, but that's the way it is now. I hope you enjoyed it anyway. So now we will continue, and the next presentation is with another key component of the Exato Pro framework, that is the runtime system, StarPU. And so we are happy to welcome Samuel Thibault of the INRIA Astan team, who will present StarPU. So Samuel, the floor is yours.
Okay, so you have my slides, right?
Yes.
Okay.
Perfect.
So I will present the ground basis of the Exato Pro framework, so the runtime system, which is called StarPU. Just to give an idea of what StarPU came from, the idea is that we have multi-core systems nowadays, which have a lot of cores, small and big ones at the same time. And that's a concern for portability and distribution of the workload. And we have specialized architectures, so accelerators, GPUs or FPGAs or coprocessors, and everything at the same time. And so we see in the future that, yes, we will keep having more or less small and big cores, and we will have to cope with this. And we have networks of such systems, so high-speed network, for instance, with some topology, and yes, we want to reach exascale, but that's clearly not an easy thing to achieve. So how do you program this? In the past, you would probably use some low-level thread libraries like pthreads or OpenMP TBB, which are low level. I mean, they have high level abstractions, but not as high as what we have seen with SCAPU, for instance. So they are quite tinkering with the hardware. So that's for the multi-core part. And for the accelerators, we've been discussing, there were some manufacturers who were providing their own APIs. So be it CUDA, OpenCL, FPGAs, depending on the manufacturers, you have different programming API. OpenCL was supposed to be a common API. as we've discussed, it's not so clear that people would stick to it. But at least it has been staying like this for like a decade. So, okay. We have OpenMP 5, which is starting to include some acceleration things. Whether it will be usable on the long term, it's not clear. We will see. But the concern we see in all of this is that it's mostly a pure offloading model. That is, you would put some work on the GPUs and not really target both CPUs and GPUs at the same time to embrace the whole system. And then you have the network. So you can use MPI, for instance, to exploit high-speed network. You can try to use PGAS, which is yet another way of expressing communications. And then you have to make all of this work at the same time, which is really questioning, because you want to take advantage of all of this, but then you have a lot of interactions between executions on CPUs and GPUs and network messages and everything. So we have task graphs. This is something which is really not new. Since the 60s, people have been working on scheduling parallelism thanks to task graphs. And this is quite new to programmers. I mean, people, when they learn C, Fortran, etc., they don't learn task graphs. They learn sequential programming. And task graphs seem to depart from this. But actually, maybe not. I mean, for people who know the Cholesky decomposition, this looks like this, and otherwise you can see that, okay, I have a matrix with several tiles, and I'm performing some blockwise Cholesky decomposition. So I work here on the first block at the corner here, then I apply some updates to the whole panel, and then updates to the rest of the matrix. And this is the source code that numeric people are used to program and know that it is efficient because it is a blocked operation, so it works best with the caches of nowadays processors. But this is also a task graph program, actually, because when you run the first line, then you actually create a task which works on this tile. And then you run the lines here, which actually creates other tasks which will work on the different tiles at the bottom of this. And we have here dependencies showing up because here we are reading some piece of data that we have written just before. So the addition of a dependency can be automated. And this is the same for the rest of the algorithm. Here we are reading AIJ, which was written just before, and etc. for the rest of the tile. And eventually you end up with a complete task graph, just coming from a sequential looking program. So I believe that's a way that we can make people work program in parallel without actually having to think about all the interactions between all of this, because the tasks have been used to express the computation in a pure way. That is, you express that, yes, this will read and write this data, and this will read only this data, and then the computer knows everything, the compilation framework, the runtime, knows everything about your computation, so it can go parallel. So the idea is to write your application as a task graph, even if it looks like a source, a sequential source code, because that will bring you the portable performance. We have been calling this in Bordeaux the sequential task flow. That is, it looks sequential, but it is still a task flow that the workshop, the framework can manipulate and optimize. So the good thing is that the algorithm remains the same on the long term. The main loops, I mean, if you go back to the Cholesky, this has been the same for decades. You can work on the sequential execution of the loop. And then if you want to accelerate on GPUs, you just need to write GPU versions of the kernels, and or just use BLAS libraries or compilers which target multiple targets, like we've seen with SkipU. From the same source code, you generate the different versions, and then the runtime will execute the whole thing. So task-based programming, that's a bit constraining because you need to restructure your code and to split computation into tasks which have pure behavior. So typically, like a BLAS call. So for dense linear algebra, that works quite well because you have the BLAS operations which are really natural to call. And if possible, we will see why later this morning. Ideally, to have stable performance so that we can have good scheduling. And the constraint is that you're not supposed to use global variables. And that's mandatory in a way when you're going to a GPU, because you cannot share a variable between CPU and GPUs in an efficient way or things like this, and a safe way in terms of synchronization. So you want to avoid this and really pass over the variables properly to the task. And actually, I would say this is functional programming, and that's maybe a good move in the end. We all know that global variables are not a good thing to use in general, and having to reach for this kind of pure programming is possibly a good thing to your program anyway. So yes, that's an interesting thing to do, I think. And then you have to accept the constraints of pure tasks and losing control. That's one thing that people are not sometimes not so keen on doing, because they want to, they know how their application is working, they know the machine, and they want to tune the execution and everything. The thing is, when you have several GPUs, you have memory management to do, you have maybe different kinds of GPUs on the same system. At some point, you don't want to do things by hand anymore. And this is a bit like when we started using compilers. We were programming assembly decades ago. And then people proposed to use compilers. And at that time, people were not so keen on using compilers because they were not sure that the compiler would do a good job. And this is a bit the same here. Maybe the runtime is not doing such a good job. I mean, not as much as if you spend several years of engineer time on optimizing, but then maybe using a runtime saves you the engineer time and gets maybe not the same performance as the best you could achieve, but reasonable performance, and then avoid the engineer time. Okay, so we have discussed the Exa2Pro stack already. So we have been discussing the composition framework just before, and the skeleton programming. So there are several ways of expressing your application parallelism thanks to this. And then you have the runtime behind, which will do the optimizations, the execution, the actual execution. On Wednesday, we will have a tutorial about StarPU that will be quite focused on how you program StarPU. That is this layer. That is how SkipU and CompU are actually using the runtime. So people could really prefer to use the high-level APIs of SkipU and CompU, of course, because it provides high-level programming. But some other people might want to directly target the runtime system because, for instance, they have already some engine that would be able to create the tasks, and it's easier to actually use the runtime system as a library than through a whole programming stack. But then it's also interesting to have a look at the runtime itself to know how it is working, to have an idea of the optimizations that it can provide. So in the context of the Exadata Pro project, we have been working on fault tolerance, load balancing, and multi-criteria scheduling. I will discuss a bit of this, but not so much. I will focus on the programming interface and the base working of StarPU. So let's give first an overview of StarPU. How does it look like? What's the idea behind it? So what we have is several CPUs, GPUs. The GPUs have their own memory. So when we have matrix A and B, maybe we have B here and A here and there, because we have several copies of them. And we want to manage this, to optimize this. And we want to avoid transfers which cost a lot. So here, for instance, we have good bandwidth between these CPUs and these GPUs, but much smaller bandwidth between these CPUs and these GPUs. So we want to optimize all of this automatically. So for this, we use a virtual shared memory. So like a bit like a distributed shared memory, but let's say virtual shared memory, because this is actually a shared memory system. And so it's a bit artificial to say this is a distributed system, but that's the idea. We have some virtual notion of where the data is. So the runtime system takes a task graph from the environment, which is on top of it. So like the SkipU and CompU compiler or libraries. And then we have the application, but it's a bit far maybe from StarPU. What StarPU will get is the task graph from some layers. And then StarPU will do the scheduling and the memory management thanks to some drivers for CUDA, OpenCL, and etc. And the idea is that a lot of optimizations can be done inside the application or inside the compilers, the piler libraries, like selecting the best implementations. But sometimes there are some things you cannot optimize statically, so you want to do them dynamically inside the runtime system. So first, we have the notion of virtual shared memory, so a bit like a distributed shared memory. So the data that is manipulated by the tasks, which are exchanged by the tasks, we want to optimize their appearance on the machine. So like we can make it show up both on the CPUs and on the GPU, so that's replication. And when a GPU, for instance, modifies some data, we want to make the value consistent. So update the value that is showing up on the CPU so that the CPU can run tasks which use the new value of the data. We have some optimizations like reductions. I will mention this on Wednesday. So basically, what you're manipulating when you're programming with StarPU is not the data itself, but a virtual reference to the data. So you're saying this data, which might actually be both on the CPU and on the GPU. And so the tasks here are not taking the data directly, like a pointer, a CPU pointer or GPU pointer. It is taking a reference to a virtual data. And then you have the tasks, which indeed take as input some virtual data and as output some data. And then it can have several implementations. So like, for instance, you have a CPU function for it, a GPU function for it, or even several of them. So that StarPU has a virtual notion of what a task is. It's a series of functions which are achieving the same kind of computation. And then the runtime can select which ones it will actually execute during the actual execution of the application. One thing is the tasks are non-preemptible. So once the function has started, we don't interrupt it, which allows to make measurements of the length of the task and maybe have an idea of how long it will take in the future. We'll discuss this later on. And then we have dependencies, of course, between the tasks, which can be set by hand by the programmer if he really wants to, but can also be inferred from the data dependencies simply. And then for us as a research team, the StarPU is a scheduling platform. That is, we have several schedulers which take this task graph, and we have a lot of research work ongoing on task scheduling thanks to this. So the code itself, we are really at the different layers than a SkiPU and CompU. We don't generate the code, the functions here. It's really a SkiPU, CompU, which generate this kind of function pointers, and then just hand them over to StarPU. And possibly you want to leverage some libraries, like if you have Plasma and Magma for CPUs and cuPLAS for GPUs, you really leverage the existing implementations of basic linear algebra operations and things like this. So you can assemble optimized implementations into the execution. So how does it look like during the execution? So we have our applications which has expressed the execution through a task graph. And so we have, on one side we have the data management, and on the other side we have execution. And then we have the scheduler and hand over the tasks to the different drivers for the different processing units. So what happens during execution? We have one task which is supposed to add A and B and store the result in A. So the scheduler decides where to put this, and it notices that we have data A and B, and we have a copy of data A in the main memory and a copy of data B in the GPU. And the scheduler knows that the task runs faster on the GPU. So it's more interesting to copy data A into the GPU and execute on the GPU than do the converse copy B in the main RAM and execute on the CPU. So it decides to put the task on the GPU because it knows it will be faster to execute. Okay, so it has to tell the memory management to copy the data A into the GPU, and then we can evict the copy that we have in the main memory because we know that it will be modified by the task. And eventually we can execute the task on the GPU, and when it's finished we can notify the application or just notify other tasks for their execution, and maybe the other tasks were waiting for the data A and they will be able to execute on the GPU, for instance. So to give a bit of history, StarPU started like 10 years ago with a PhD of Cédric Ogonnet. So it's like 17,000 lines of code, of C code. It's available under an LGPL license, so it can be combined with proprietary software. It's an open source project, so there are nightly tables. There is a GitLab page to contribute source code and issues and everything. So it's really open to contributors. And it's really recognized as state-of-the-art software because the Crown paper has been cited more than 1,000 times. So it's really a success. We have been able to port a lot of applications on top of StarPU, like QRMEMS is QR sparse linear algebra solver, and initially they were using their own implementation with a 1D decomposition, and when they moved to task and a task version of QRMEMS, then decomposing into 2D was really much easier, and they had a lot of parallelism, and we are able to control the memory used by the solver because it goes out of memory. Otherwise, it is really something that is working nice. And we have been working with Airbus for their dense but compressed linear algebra solver H-matrix, because StarPU provides an out-of-core support, which allows to run a 1 TB.6 matrix when the machine only has 200 gigabytes of memory. So that's really leverage for them, because they don't need to care about the memory. It's all handled by the runtime. And we have implemented CFD, FMM, CG stencils. We have a lot of examples. We support various architectures. So we have NVIDIA and OpenCL, of course, the Xeon Phi. We have FPGA, so which was worked on the Exadata Pro project. We have some experimental ports for some old architectures, and we support different operating systems, so including Windows, even if it's quite difficult to program with this, but yes, it does work. And then once you have ported your application to tasks, you have all of this for free. I will discuss some of these this morning and on Wednesday. So of course, task scheduling, so pipelining the uploading of data and the execution of the tasks, and balancing the load between the execution and the need, and prefetching the data. We have some analysis of the performance, whether this is the bounds that we can, theoretical bounds that we can compute according to what the application is, to compare with actual execution times here. We have distributed execution. I will discuss this. Some performance analysis tools out of core. We have seen this. And we have even simulation here, which we'll use on Wednesday, so that you can work with TAPU, even if you don't have a GPU, to experiment with GPUs, even if you don't have it. Okay, so first let's talk about task scheduling. Task scheduling is really something you want, because static mapping is not an easy thing, and simple task scheduling is too simple. So for instance, here we have CPUs which take a long time to execute the tasks, and if you use a simple dump strategy, then you end up having a lot of idle time here, because the CPUs have started their task and we are waiting for them, while the GPUs here would have finished the tasks in a much shorter amount of time. So you really want scheduling to avoid these kind of situations. In StarPU, a scheduler is simply something you push the ready tasks into, and then the workers, so CPUs and GPUs, are pulling some tasks from the scheduler. So we have these push and pop operations, and then the scheduler can do whatever he wants. So it can be a single list that you push the tasks into, and the workers just pop from it. Or you can decide ahead of time which of the CPUs or the GPUs will execute the task. So it allows to not really predict, but to work out the future, to say this will go there. And this allows to preload the data on the GPUs, for instance, because you know that this task will execute on the GPU, so you have time in the meanwhile to load the data on the GPU. Maybe you do not want to decide all the scheduling decisions in advance, because maybe you will want to see what will happen in the future before making a decision. So this is really where we are doing our research work. Just to give an idea, for instance, here I'm showing the classical heterogeneous earliest finish time. If we have an estimation of the task durations, we have here what we have decided to do in the future. So we know that CPU 1 will do these 2 tasks, and that will take this amount of time, and the same for all other execution units. And then we have a new task to schedule. And this new task will take a long time on CPUs and a much shorter time on the GPUs. So then we decide, because it will terminate earliest on the GPU, to schedule it on the GPU. And that's fine. But maybe it will take time to transfer the data to the GPU, because here on the platform, it actually takes a long time because of the bandwidth. And then we add the transmission time here, and we notice that, okay, maybe the GPU is not so interesting because it takes time to move the data there, and then we will actually move the task on the CPU. So this is really making a balance between acceleration and data transfers. And we have had a lot of interesting results thanks to this. So for instance, here, we have the execution performance with 1 GPU, 2 GPUs, 3 GPUs, and 4 GPUs. And we've seen that we get linear performance improvement, almost linear. But the interesting thing is that here, when we add the CPUs in the play, we get 200 gigaflops more. So as much as the other GPUs. This is an old experiment. That's why 200 gigaflops is not that high. But the interesting thing is, if you run the application on CPUs only, you would get only 150 gigaflops. So that means that if you use CPUs alone, they give this performance. But if you add them to the execution with GPUs, they bring 200 gigaflops performance improvement. And that's thanks to heterogeneity, because it's not actually the CPUs which are providing this performance, but because they are actually relieving the GPUs from the tasks that GPUs are not good at. That's thanks to heterogeneity, actually. Because what happens is that we have tasks here which are much faster on GPUs, and not so much fast, and those tasks which are not so much faster on GPUs. So the scheduler notices this and thinks, okay, I will put these tasks on the GPU so that the other ones are done on the CPU, and then we get a super linear effect. Okay. The second thing I wanted to present today was the support for clusters. So how can you scale over MPI? So we've seen the scheduling inside a node, but then how do you schedule over MPI nodes? You can try to do this by hand, so splitting the task graph. So inside your application task submission code, you would have to split, but it's really not flexible. You want something easier to program. There are some proposals to use master slaves, but that doesn't usually scale because the master will have to tell every slave what it has to do. So for exascale, this is not really a solution. So it's better for each node to actually determine by itself what it has to do. So to really have a distributed execution, distributed decision of what should be done. Parsec for this, to achieve this, use an algebraic representation, which is quite difficult to write because you have to really formalize your application, and that's not the way people are used to program. And sometimes you just cannot express your application. So what we have been doing is to just enroll the whole task graph on each node. What I mean by this is the application distributes the data on the MPI nodes, and then StarPU will make the will work out the coherency between the MPI nodes. So all nodes process the whole algorithm. They go through the whole algorithm, but then determine which part of it has to perform and which communications are needed to actually exchange the data between the MPI nodes. So what does it look like? We have this algorithm we have seen at the beginning, which entails this task graph. And what you do is to say this tile will go on this rank. So for instance, here, this is the formula for 2D block cyclic distribution, which is really common in dense linear algebra. And then by just adding these few lines before the submission of the task graph, then StarPU knows that it has to split the task graph into pieces on different nodes. So the main algorithm is not modified. You just selectively say this goes there, and this can easily be modified without having to change the algorithm at all, to change the distribution of the data and thus of the tasks. So the task graph is done by everybody, and you provide the data node mapping. You can modify it during the execution to migrate the data. And then the mapping of the task will be done by the runtime. So that really separates the concern of what is my task graph to get parallelism and what is my data mapping to reduce the communications. And then everything will be done automatically and in a distributed way. We don't have synchronization. We don't have global scheduling that would make it a central point that would not scale over exascale. Just to give an idea, here I have node 0, which looks at the task graph, but only actually submits the tasks for its own node and submits the reception of this data dependency. And on node 1, at the same time, it looks at the task graph and determines that these tasks are for him, and it will have to send the data of the output of this task over to the other node so that it can actually get the result. So all of this is done in parallel without global synchronization. This is the kind of results that we've been having with this paradigm. So this is an execution with only CPUs, and this is the execution with GPUs. And we see that compared to Scalepack, we have a much higher performance. This is a logarithmic scale, so this is really much better than Scalepack. And here the two curves are the Chameleon, so that's the StarPU version of the dense linear algebra. And here dPlasma, so PTG, that's the algebraic expression of the same computation, and both achieve indeed really interesting performance. And even with GPUs, we do get a really interesting performance, so over 144 nodes. Just to mention quickly the simulation that will be used for the tutorial on Wednesday. So the idea is that we have calibrated with the actual execution of the application on an actual hardware, and then we got some performance profiling of the behavior of the application. So we have run this just once on the platform. And then we provide you with these performance profiles, and you will be able to run the application with StarPU just from the task graph of the application. And then with a simulator, get simulated execution times. So that allows to run performance with GPUs and everything on your laptop. And it's even deterministic. So we are sure that you do get the same result as we expect. And it is really accurate. So you rebuild and run again. So this is the performance you get. So the native is in plain line and the simulation is in dotted line. So these are different scheduling algorithms. We see that they have different behavior, and more importantly, we see that the simulation really provides a good representation of the behavior of the scheduler. So it's really interesting for us because it's much faster to execute like this instead of waiting for the computation to run, which just simulate the computations. It's reproducible, so these curves, we can actually reproduce them. We just need the performance models and the application, and we can run the simulation again. We don't have to reserve the TACAT system to have an SSH configuration and everything. And we can modify the system architecture. We can maybe modify the size of the GPU to see whether with here it's the matrix size, and maybe that's because the GPU is small that we have a performance reduction. And so we can tune the parameters to see how well it behaves. And we can really play with this like this. So to conclude, the task graph abstraction is really a nice programming model because you can really here at this level have something which looks like a sequential program. SkipU and CompU can create a task graph from the application. So in both cases, it's the same abstraction that provides the shape of the application, the computations, an idea of how long the task will take, and then do some advanced scheduling. So we can optimize the execution on GPUs and FPGA accelerators and over the network. So for us, it's really a playground for scheduling, fault tolerance statistics. So this is what we have been working on in the ExaTrue-Pro project. And this is aimed at a lot of different kinds of applications. So we have some examples in the ExaTrue-Pro project, but also others that we have been having with StarPU by itself. So on Wednesday, we will have tutorials. So there's a GitLab page which contains the precise materials with explanations and some results. But I would like to emphasize that this will run in a Docker container to have all the dependencies installed and everything. So please follow the Getting Started guide and to have this ready before the tutorial, because it takes a long time to build. So in the timetable of the EOCO and ExaTrue-Pro event, you have this guide, and you have section 2 about installation. It takes like half an hour or even an hour. So you want to run this ahead of time. Maybe we can put the resulting image available for download, but that's like 3 or 4 gigabytes image. So maybe you want to build it by yourself. We'll see, but at least look at getting these things ready before the tutorial, because otherwise we will lose time and it's not interesting. You just run and it runs by itself. You don't have any action to do during this half an hour or now. Okay, so that's all for me, and I welcome any questions.
Thank you very much, Samuel. So we have time for questions. Anyone? Okay, no question. So maybe I will have one question. In StarPU, what is the scheduling policy of different tasks? Do you have parameters? Can you really control it, or is it, I would say, built in and you cannot do anything?
Well, actually, you can provide your own scheduler.
Okay.
The scheduler is a pluggable thing in StarPU. So we have a series of different kinds of schedulers. So work stealing, heft, and others like this. Hetero-Prio, which takes a different approach to heft. But the application can even provide its own scheduler. The idea is really to implement, like I've shown, basically you implement the push and pop operations, and then you can do whatever you want inside your own scheduler. So some people have been doing this. So for instance, hetero-prior, which I've mentioned, was originally for a fast multipod method, because the state-of-the-art algorithms, scheduling algorithms, were not so good at it because it's a bit peculiar of an application. So the PhD student who was working on FMM with task-based programming just wrote his own scheduler, and now it's part of the different schedulers available in StarPU. And then you can also guide the scheduler. You can tell these tasks should really go to the GPUs or should really go to the CPUs. This is a priority for a task. So really these tasks do them before the others. So to really sort the task in the different containers. So that's that part of our research to see which kind of clues the application can provide to the runtime to optimize the execution.
Thank you. We have a question by Carlos. Please, Carlos, go ahead. Carlos, we don't hear you. Did you have a question? Because I see your hand raised, but I cannot hear you.
Yes, your microphone is open in Zoom, but maybe not on your computer.
Hi, can you hear
Right.
me now?
Yeah. Yes.
Hi, I have a question. How I understand the scheduler needs some time to process to do the scheduling, and how large should be the tasks in order to make this neglectable?
That's a really important question indeed. What we usually notice is like a dozen microsecond overhead per task, which is actually the overhead of CUDA. CUDA has this kind of overhead. So if your tasks are only 100 microseconds long, it will be hard to get good performance because the overhead of the runtime will be large. If your tasks are at least 1 millisecond long, then yes, it becomes neglectable, that overhead of the runtime. So we have seen people having tasks which last for 1 second or something like this, then that's really for free. We have seen some people with 10 microseconds tasks, then StarPU is not a good thing. You would have to use an intermediate layer that collapses tasks together to group them and to build something bigger, and then it becomes an acceptable overhead of a runtime.
This grouping, can I specify, for example, to be executed in a specific hardware?
I'm not sure to understand. I mean, SkipU, for instance, will do this kind of grouping for you, and it will create large tasks to hand over to StarPU, and then it can work on any kind of architectures that SkipU can build the skeleton for.
Okay. Yeah, and another question that I have is recently I have been reading about one API from Intel. How is different StarPU, or how different is one API from StarPU?
I haven't looked at the details of one API, but we've been seeing task-based programming for a decade now, and all those APIs are basically all the same, more or less. The kind of thing which is really different in StarPU is the scheduling. I mean, we really aim for integrating the state-of-the-art of task-based scheduling. So the HEF scheduling, hetero-prior, and all of these, which notably look at the expected performance of tasks. Not many runtimes do this kind of thing, and we try to do this really. We try to make the balance between the time to transfer data and execute the task, and quite often the runtimes make a good job at having good enough heuristics, eager heuristics. Here we try to do more than just this and get even if possible provably good performance. Like, you know, we know that Eager has some provably proved bounds on the lower bounds on the performance, and we would like to be able to achieve this kind of thing with an actual runtime, not only in theory. We have the theory that does this, but to do it in a real runtime.
Okay, thank you.
And maybe one last question by Mathieu.
Yes, thank you, Samuel, for this presentation. With one of my postdocs, we have started to study the task-based methods for maybe a few months, 6 or a bit more. And to start, we have decided to use the OpenMP task. But we had the idea actually to test at some point the StarPU runtime. And I was thinking, do you have some, if someone has OpenMP task-based code, do you have advice? Is it we can just take the same philosophy and apply the StarPU one, or there are some little things we should pay attention to?
And actually, we have an OpenMP compatibility layer on top of StarPU. So if you go to the StarPU website, you will see some links to, so it's called KStar. So KStar will take your OpenMP code and generate the StarPU code, corresponding StarPU code. And on an FMM application, we did get the same performance actually between the OpenMP and native code, except that we added commute access to the data in the StarPU code, and then it improved the performance. And then we added the Pragma commute to the OpenMP programming model, and we got the same kind of performance improvement. And it's being standardized, I think, in the current standards. So basically, yes, OpenMP is kind of proxy to task-based programming, and maybe you can stick with the OpenMP programming model. The good thing being that you can use whatever runtime provides the OpenMP interface.
Okay.
If you want to go to StarPU itself, because, for instance, there is some feature that is not available yet with the OpenMP language, then you would have to move, indeed, your program to use StarPU API. But the principle will be basically the same. The splitting of the task will be clearly the same, I believe. The expression will be different because you're using a library, a C library, and not a language. So it's more verbose. You have quite a few lines of code to express that you have some code to be inlined into a task. But otherwise, the main structure of the application will be the same. Usually what I see is an application in which the computation is already separated into functions, pure functions. Then it's easy to move from one task-based programming model to another, because you just rewrite the main source code, but that's not so big quite often.
Okay. Thank you.
Okay, thank you. Thank you again, Samuel. I think we have to stop for the lunch break.
Yep.
Just one last thing. As you mentioned, Samuel, and as did other speaker, I think it's very important that all participants install all the required features on their computer for the hands-on tomorrow. So please do so. Ask if you have a problem installing it. But so tomorrow, when the hands-on start, we want to be able to start right away and not lose much time with installing all the required tools. So please do so before tomorrow. Thank you very much. Thank you to all the speakers. Bon appétit à tout le monde, and we reconvene a bit before 2 o'clock for the next session. Bye.
See you later.